Hey there! I'm so happy to see you again. In this video, we want to talk about OCD in machine learning. It happens when our AI memorizes the data we gave it instead of learning a general idea from it. But before taking a closer look at this problem, let's start with the general idea of learning in machine learning. You see, until now, we always talked about giving our AI data and let it learn from that. But is that really so simple? How can we be sure at all that our AI is learning something useful instead of just obsessing over something irrelevant? We better welcome one of my friends to get to the bottom of that topic. Say hello to my friend Apprendi. Alright, so we have got this huge pile of random data, let's say these books. And we want our AI to make sense of it. Likely, we have several piles of data, even a whole bookshelf, and want our AI to look at all of them successively. You know that we are used to humongous amounts of data nowadays. So splitting up might be a good idea. For convenience, we could use a name for the time our AI needs to work through one pile. And if you have ever tried out one of the common AIs, you know that it takes forever for them to finish. Based on that, how about we call the time to process a whole pile an epoch? Sounds fair to me. And like I said, most of the time, the pile is huge. Really huge. If it takes an epoch to process all that, what if in the end we realize that our AI learned something wrong? We clearly do not want that. It would be wiser to split up the pile and check for progress regularly. That being said, we split our dataset into batches. For example, smaller piles of books. Our AI will then go through each batch separately. And after each batch, we check what the AI has learned. Good idea, don't you think? The number of data points we put in each batch is the batch size. In this example, it could be the number of books. This batch size can vary a lot between different AIs and use cases. Hence, this is one aspect we have to adjust every time we create a new AI. Just like before, we need to have a name for the time it takes to process a batch. How about iteration? If it takes one iteration for each batch we have, that means we have as many iterations as we have batches. I love it. With these names, we can talk more precisely about what happens during training. Let's sum it up real quick. We need an epoch for a whole dataset that is split up into different batches, and processing one batch is called an iteration. After each batch, we check what the AI has learned, and after the whole epoch, we draw our big conclusion. Awesome! That sets the general procedure of our learning. But how do we actually check if our AI is learning something useful? One of many possible approaches is the Holdout method. In general, it is common practice to divide our dataset into two smaller sets. One set consisting of all the data the AI is supposed to look at and learn from, the training set, and another set that we call the test set, which the AI will tackle after some time to test how well it performs on data it does not know yet. The idea? With the training set, our AI is free to take all the time it needs to learn as much as it can from it. The test set is somewhat like an exam. No assistance allowed. Let's see how well you studied. A common split would be 80% training set and 20% test set. This might differ depending on the amount of data you have, though. Small data sets may need a bigger percentage for the test set, while bigger data sets can get away with maybe 1% test sets. It always boils down to us being aware if our results make sense and act likewise. If you are more familiar with the topic, there's also a third pile, the validation set. But I won't go into detail here. For starters, training and testing suffice to understand the main idea. Alright, so the AI jumps between learning and taking exams all the time. But how often does it need to prove itself? Guess what? It is up to you. If you feel like it, it will show you its progress after each batch. Otherwise, it will take an exam after each epoch. You remember, right? An epoch is the time we need to process the whole dataset. And normally, we do not go through the whole dataset once, but several times. This is why in most of the common AI models, we define the number of epochs we want the AI to perform. We then monitor how well it does on the test data. Ideally, we do not need as many epochs as we thought for it to be proficient. But that again is up to you, your use case and your definition of proficiency you need the AI to achieve. However, what if our dataset is not big enough to divide it into two smaller datasets? It can happen that the dataset is so small that after each test, the results vary a lot. In this case, experts say that the variance is too high. And to solve this problem, we need to try out something new. And this something new might be the so-called k-fold cross-validation. The idea here is that we split our dataset into k different smaller sets, often 5 or 10. Then we go through several epochs, and each time we use another sub-dataset as the test dataset. So, as an example, we split our dataset into 5 smaller datasets. Let's call them setcitos. We use blue for the test dataset and red for the training dataset. And in the first epoch, the first setcito is used as the test dataset. All the others are used as training data. In the second epoch, the second setcito is used as the test dataset, whereas the others and the first setcito are used for training. This goes on until each setcito has been used as the test dataset once, and there we calculate an average over all these epochs. Like this, we are able to test our AI with all our data, step by step. Now you have seen that we split our data into smaller piles. The extreme case is that each pile consists of only one element. In our example, only one book. This extreme case is called leave one out cross-validation. In this case, we will use each data point one set alone as the test set for one epoch. Here in our example, that would mean that we took each book as a single setcito. And each round, there would be exactly one book for our AI to use as a test set. This choice is appropriate for small datasets. Alright, we defined the epochs, the iterations, and the batches inside it, the training and the test set. And how to divide them with the holdout and the k-fold cross-validation methods. That is a pretty good start, I would say. Knowing and doing all this does not guarantee us good results, though. There are two very infamous phenomena that can occur while training AIs. So let's talk about over and underfitting. If you remember my video about linear regression, you know that we compared the R-squared score of different models on different datasets. I told you that some models describe the data better than others, and it shows in the R-squared metric. The overall goal of machine learning is to find models that describe our data well in general. That means that it is supposed to describe our current data well, but should be flexible enough to be prepared for new data. This generalization can overshoot the mark, though. Let's throw some data to the screen to better understand what is going on. Here we see a lot of data points of how the value of something, example given a car, changes over time. And now we let a random AI try to describe the data with a mathematical function. Let's see. In this example, the model catches some lower and very high data points. But it completely misses the ones in the middle and at the bottom. The model is too generalized. We call this underfitting. It is under the desired fit. The opposite would be that the AI memorizes the training data so well, it describes the data perfectly, but is not generalized at all. Seeing it for the first time, it looks like a solid solution, don't you think? The problem is that this model tends to perform horribly on data it does not know yet. Take these exemplary data points of the test dataset for example. If we now look at how far they deviate from the function our AI proposes, we realize that they are really far away, even though they are positioned closely to the overall progression. That is not really a good solution, to be honest. This we call overfitting. Our AI performs over what we would desire. A good fit would look like this. Here we see that the function follows the data in a general way, but does not cater to every point specifically. If we put in the same new time values, the AI would return realistic values that are closely related to the ones it has learned with. So, lesson learned, avoid over and underfitting. Unfortunately, these two phenomena are quite common in the daily life of a machine learning engineer. That is why you should be aware of them and always act cautious if your model performs too well. One good indicator is a discrepancy between your training and your test data. Let's look at a graph where we see the accuracy of our metrics over time. If your AI tells you after each batch that it recognizes the training samples with an accuracy of over 95%, but the accuracy it achieves on the test set stays way below, let's say 70%, then you can be pretty sure that you are encountering overfitting. Your AI memorizes your data instead of generalizing from it. There are different ways of tackling this issue. You could use more data, for example. Or, if the holdout and the cross-validation we talked about do not work, there are some mathematical techniques to help you. For example, the rich or the lesser regularization with which you punish your AI for adapting too well to the data. But these we will deepen in another video, because they need to be explained. If you are already curious, I will put some links into the description. For now, we call it a day. Thank you so much for watching. Feel free to watch my other videos too. Have a great week. Bye.